Find the maximum moment at point A in kip feet. In this problem, the height to the center of an elevated water tank measures 80 feet. For the tank, the lateral stiffness, K, and the weight, W, are also provided. The tank experiences a lateral force, P, which is characterized by the plot as a function of time. The maximum moment at point A will equal the maximum shear force caused by the loading times the height to the center of the tank. Since the height of 80 feet is known, we need to solve for the maximum shear force caused by the loading. The maximum shear force equals the lateral stiffness, K, times the maximum lateral displacement, U0. From the problem statement, we already know the lateral stiffness, but we need to determine the maximum lateral displacement. The displacement of the tank as a function of time depends on the tank properties and the tank loading. The response of a system, U of t, has been determined for various standard loading patterns, such as the ramp up to constant, the half sine, and the triangular pattern. Although the forcing function in this problem could be a combination of multiple triangular shape patterns, we're actually just looking for the maximum displacement, U0, which is independent of time, and we can take advantage of the short loading duration, TD, which equals 0.08 seconds. If the loading duration is less than half the natural period of the system, then the loading pattern can be approximated as an impulse, and therefore maximum displacement can be approximated as the impulse, I, divided by the stiffness, K, times 2 pi divided by the natural period of the system, T sub n. But first we must calculate the natural period of the system to confirm if this approximation is valid. The natural period of the system equals 2 pi divided by the natural circular frequency of the system, omega n. The natural circular frequency equals the square root of the stiffness, K, divided by the mass, m. We already know the stiffness equals 8.2 kips per inch, and we can determine the mass by dividing the weight of the tank by the gravitational acceleration. The mass of the system equals 0.052 kips seconds squared per inch. This makes the natural circular frequency equal to 12.56 radians per second. Using this value, the natural period, T sub n, equates to 0.50 seconds. Therefore, it is true that the time of duration, Td, of 0.08 seconds is less than half of the natural period of the system, and we can use the approximation for the maximum displacement of the system by approximating the load pattern as an impulse. In this equation, for the maximum displacement, we already know the stiffness K and the natural period of the system, T sub n. But we don't yet know the impulse, I, which is quantified by a force times a time. We can compute this impulse by summing up the area under the loading curve, P times T, by computing the 4 separate areas in discrete time periods every 0.02 seconds. As an example, area 2 equals 0.56 kip seconds. After summing all four of the impulse, I equals 1.20 kip-seconds. With the impulse value known, we can solve for the maximum displacement of the system, which equals 1.838 inches. This value for maximum displacement can be plugged into our equation for maximum shear, which computes to 15.07 kips, which is then plugged into the equation for the maximum moment at point A, which equals 1,205 kip-feet. When reviewing the possible solutions, the answer is C.